This is an online learning (LMS) project. The task course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Content: angle modulation, PM and FM. Comparison of amplitude and angle modulation. PM and FM description. Frequency modulation. Narrow band FM, wide band FM, and bandwidth of FM. Examples of FM modulation techniques. CW modulation, sinusoidal carrier. Linear amplitude modulation M. Nonlinear exponential lower angle modulation, frequency FM, phase PM. Continuous wave modulation is done using a sinusoidal carrier. There is a linear and nonlinear type. Pulse modulation, pulse carrier. PAM, pulse amplitude modulation. PWM, pulse width modulation. PPM, pulse position modulation. Pulse modulation is done using pulse carriers. There are different techniques making use of amplitude, width, or position modulation. Angle, FM/PM, modulation. Consider the signal A, C, cosine theta of t. Carrier has constant amplitude A. C angle, which consists of the frequency and phase, is varying with time. F frequency varies only. We have frequency modulation and phase modulation if the phase is varying to convey information. Amplitude versus angle modulation. Consider linear continuous wave amplitude modulation. Examples are M, DSB, SSB, VSB. Transmission bandwidth never exceeds twice the message bandwidth, 2W. Signal-to-noise power can be increased only by increasing the transmitted power, SD. Consider nonlinear continuous wave angle modulation, such as FM, PM. Transmission bandwidth much greater than twice the message bandwidth. Signal-to-noise power can be increased without increasing the transmitted power, SD. So, amplitude versus angle modulation choice is a trade-off between power and bandwidth. Question: amplitude versus angle modulation, properties. Compare the linear modulation schemes, AM, DSB, etc., with nonlinear modulation schemes, FM, PM, in terms of the following: transmit power, superposition of modulation, visualization of the message signal. Solution: transmit power varies with the modulating signal in linear modulation schemes, whereas, in nonlinear modulations, the power is always fixed, irrespective of the modulation sensitivity or modulating signal. In linear modulation schemes, the superposition of modulated signals holds. That is, if you sum two signals and modulate them, you should get the same result as first modulating them separately and then summing them. This property is not valid for nonlinear modulations. Visualization of the message signal. In linear modulations, by looking at the transmit signal, you can moderately see the envelope, thus the message signal. But in nonlinear modulations, this is not possible. So, the extraction of message signal in nonlinear modulations are more complex compared to linear ones. PM and FM. Take the signal as S of t, A, C, cosine theta of t. Instantaneous frequency is found to be the derivative of theta of t with respect to t divided by 2 pi. Theta of t is equal to 2 pi fct plus phi c. In phase modulation, instantaneous angle varies linearly with the message signal. Kp is the phase sensitivity. In frequency modulation, instantaneous frequency varies linearly with the message signal. Kf is the frequency sensitivity. Question: PM and FM. Consider the simple message signal m of t equals t, where t is continuous time index. For this message signal, find the angle theta I of t for FM and PM. Also, find the instantaneous frequency for both cases. Take phase sensitivity factor K, P, as pi over 2, and frequency sensitivity factor K, F, as 1. For simplicity, assume baseband operation. Finally, draw the transmitted signals for both cases. Solution: this example clearly shows that the frequency is the accumulated phase. FM signals tone modulation. This is a nonlinear process. T has a more complicated spectrum, and that of AM2 makes spectral analysis easier. Consider the simplest case, tone modulation. Tone modulation is the case when the message signal to be modulated is just a sinusoidal deterministic signal. Message signal m of t is equal to a m cosine 2 pi fm t. Fi of t is equal to fc plus kf a m cosine 2 pi fm t kf times a m can also be written as delta f, which is frequency deviation. Using the results from previous slides, we get the signal to be transmitted s of t as a c cosine of 2 pi fct plus beta times sine 2 pi fmt, where beta is delta f over fm. When beta is much smaller than 1 radian, this scheme is called narrowband, and when it is much larger than 1 radian, it is wideband. Question: FM signals tone modulation. Consider a message signal m of t equals cosine 2 pi 10 t. This signal will be frequency modulated with the frequency sensitivity of k, f equals 1 Hz. Write the expression for transmitted signal s of t, clearly stating all of the parameters. Assume an arbitrary carrier frequency fc, narrowband FM. Consider the narrowband FM case. Beta is much smaller than 1 radian. Then in this case, using some approximations of trigonometric functions, we can write the signal s of t in a compact form as a c cosine 2 pi fct plus 1/2 the beta a c times in parenthesis cosine 2 pi fc plus fmt minus cosine 2 pi fc minus fmt. Narrowband FM spectrum. Remember, we can write amplitude modulated signal in a very similar manner with narrowband frequency modulation. The only difference is that instead of beta, there is mu, and the sign of the second cosine term is positive. Comparing the one-sided frequency spectrum of these two signal types, we see the similarity once more. Question: FM signals tone modulation spectrum. Write down the frequency domain representation of the following signal s of t equals cosine 2 pi 1000 t plus 1 over 10 sine 2 pi 100 t. Solution: this signal is a frequency modulated signal. Modulation index beta is much smaller than 1 radian, so we can write the frequency domain representation in the following fashion. S f equals a c delta f minus f c plus a c beta over 2 delta f minus f c plus f m plus delta f minus f c minus f m. Wideband FM. Now, let us consider the wideband FM, where there is no restriction on beta. S of t is defined as a c cosine 2 pi f c t plus beta sine 2 pi f m t, just like in previous slides. Also, keep in mind that we assume a carrier frequency fc much larger than message bandwidth fm. Write s of t in the form real part of s tilde of t times exponential j 2 pi f c t, where s tilde of t is a c exponential j beta sine 2 pi fm t. As we learned in previous lectures, we can write this s tilde of t expression in Fourier series after some calculation. Fourier series coefficients c and are found as a c times j n of beta. J n of beta is a well-defined mathematical function called the Bessel function. Its values for any n and beta can be found on a Bessel function table, which is also provided in following slides, so you do not need to calculate this integral all the time. After expressing s tilde of t Fourier series, it is trivial to get to the s of t, which is equal to a c times summation over all n j n of beta times cosine 2 pi in parentheses f c plus n f m times t. Writing practical wideband FM signals in this form is explained in following slides. This transformation of Fourier series is done, basically, to ease the calculations of FM spectrum, which will also come in following slides. Bessel functions, taking Fourier transform of the signal s of t, we derived earlier. We get a c over 2, summation from minus infinity to infinity jn of beta, Dirac delta f minus fc minus n fm, plus Dirac delta f plus fc plus n fm. Jn of beta is the Bessel function, and it has this property for all n. Numerical values of the Bessel functions at different values can be read from a table, like this one. Question: wideband FM, sinusoidal input. Consider a message signal, mt, equals cosine 2 pi 25,000 t. This signal will be frequency modulated, with the frequency sensitivity, k, f, equals 25,000 Hz over volt. Write the expression for transmitted signal, s of t, clearly stating all the parameters. Assume a carrier frequency, fc, of 100 MHz. Leave the summations as it is, once you have a closed form expression, with all the parameters shown explicitly. Solution: in previous parts, we have an approximation coming from the narrow band assumption. Now this assumption is gone. Write down the general formula for this question, and check the Bessel function table to determine how many terms in the summation you should use for an accurate result. In this case, taking n equals 3 should be sufficient. FM signal spectra. Average power of FM signal is 1/2 a c square, sum of n from minus infinity to infinity jn of beta squared. FM spectrum consists of a carrier frequency line, plus an infinite number of sideband lines at the frequencies fc plus nfm. All lines are equally spaced by the modulating frequency, and the odd-order lower sidebands are reversed in phase or inverted relative to the unmodulated carrier. In a positive frequency line spectrum, any apparent negative frequencies, in other words, where fc minus nfm is smaller than 0, must be folded back to the positive values. Question: wideband FM spectrum, sinusoidal input. Consider the wideband FM signal s of t. Find its frequency domain representation as f, and draw its amplitude spectrum. Solution: extract the relevant parameters step by step. The parameters you need are beta, a, c, f, c, and f, m. These are all given in the question explicitly. Put them in the general power spectrum formula for FM, and then draw the amplitude spectrum. In this slide, take the amplitude of the power spectrum as f. Keep in mind that any negative frequency content will be folded back to its symmetric value over the origin. That is, the Dirac delta content of the minus frequencies will be folded back to their corresponding positive frequencies, and the overlapping terms will be added up. Also, keep in mind that there will be no negative content with respect to y-axis, that is the negative terms, in the summation, if any, will be made positive. FM bandwidth. Bandwidth of an FM signal is given by beta, which is approximately 2 delta f plus 2 FM, which can also be written in the form 2 delta f times 1 plus 1 over beta, where beta is delta f over FM. This is known as Carson's rule. Question: FM bandwidth. From Carson's rule, find the approximate bandwidth of the FM signal with parameters delta f equals 10 and message frequency equals also 10. After finding the Carson's bandwidth, check the spectrum of the signal for visual bandwidth and comment. Solution: Carson's formula states that the bandwidth is 40 Hz. By visual inspection, we also see from the spectrum that the bandwidth is approximately 40 Hz. Note that, strictly speaking, FM has infinite bandwidth because of the Bessel function's behavior, but it can be approximated well accurately by Carson's formula. FM generation. Now the problem is how to generate FM signals, controlling the frequency by a voltage applied to the variable capacitor, is done according to this formulation. Phi of t is equal to 1 over 2 pi square root of L1 plus L2 times C of t. C of t can be calculated for an input signal cosine 2 pi FM t, as C of t is equal to C0 plus delta C cosine 2 pi FM t, and his case output frequency Phi of t is F0 times square root of 1 plus delta C over C0 cosine 2 pi FM t. Unmodulated signal frequency F0 is equal to 1 over 2 pi square root of L1 plus L2 times C0. Denote delta C over C0 as minus delta F over F0, then Phi of t is approximately equal to F0 plus delta F cosine 2 pi FM t. The block diagram is shown here for a wideband FM wave. The disadvantages of the setup are oscillator stability issue, frequency deviation issue, and input voltage-output frequency ratio issue. Question: FM generation. Find the capacitance and inductance parameters for a Hartley oscillator in order to generate an FM signal with carrier frequency of 100 MHz and frequency deviation of 1 MHz. Choose your capacitor and inductor values, C0, L1 and L2, from the list. Determine the varying capacitance value, delta C, yourself. Take the inductances L1 and L2 equal frequency demodulation/detection, PLL. Either use direct demodulation or indirect demodulation. Indirect FM demodulation is called phase-locked loop, PLL. PLL is used in synchronization and frequency division or multiplication. It consists of multiplier, VCO, and loop filter. Initial conditions are VCO frequency precisely set at unmodulated frequency, FC, and VCO output has 90 degrees phase shift with respect to the unmodulated carrier wave. Take input FM signal S of t as A, C, sine 2 pi FC, t, plus phi 1 of t. Phi 1 of t is equal to 2 pi kf times integral from 0 to d, m of tau, d tau. In this case VCO output is R of t, which is A, V, cosine 2 pi FC, t, plus phi 2 of t. Let V of t be the control voltage. Then, phi 2 of t is 2 pi kV, integral from 0 to d, V of t, dt. What we talked about is implemented this way. Superheterodyne, superhet, receiver. Superheterodyne receiver block diagram is given here. Table shows some parameters for typical AM and FM modulation systems. Superheterodyne, superhet, receiver. Mixer part is called down converter. There are two distinct amplification and filtering sections prior to demodulation. The incoming signal XC of t is first selected and amplified by the radio frequency, RF, section tuned to the desired carrier frequency FC. The RF amplifier has broad bandwidth BRF, so it partially passes adjacent, neighboring, channel signals along with the desired signal XC of T. A frequency converter, down converter, comprised of a mixer and local oscillator, translates the RF output down to an intermediate frequency where if is smaller than FC. The if section removes the adjacent channel signals using a fixed bandpass amplifier called if strip. The if output goes to demodulator or detector to recover the message signal. Then the audio amplifier is used to amplify the baseband signal. Superhet receiver, spectral analysis. The RF spectrum includes the desired signal, plus adjacent channel signals on either side, and another signal at the image frequency. This phenomena is depicted here in this graph. Superhet receiver, image frequency. There are two outputs of the mixer, which are FC minus FLO, or FC plus FLO. Image frequencies for a station at FC are FC plus 2F IF or FC minus 2F IF. Question: Superhet receiver. An FM superhet type receiver operates at an intermediate frequency of 10.7 MHz. The carrier wave of interest is located at 100 MHz. Find the local oscillator value for the down converter. Assume local oscillator to be greater than carrier frequency, high side injection. Also, find the image frequency and propose an appropriate RF bandpass filter. Bandwidth of the FM signal is much smaller than bandwidth of RF bandpass filter. Solution: RF bandpass filter should be centered at carrier frequency and has an appropriate shape that does not allow any of the image frequency content to be passed. Receiver, RX, specifications. Dynamic range is the difference between largest and lowest signal levels that can be detected without distortion. A number around 100 decibels is typical in communication systems. Big numbers are good for this parameter. Sensitivity is the minimum signal level that can produce a specified signal-to-noise ratio, SNR, at the intermediate frequency section. This parameter dwells about -100 dBm. The lower the value, the better the sensitivity. Selectivity is the ability to discriminate against the adjacent channel's signals, also called, in some cases, adjacent channel rejection ratio. It is expressed in dB scale. Any number around tens of decibels is good. Noise figure indicates how much the receiver degrades the input signal-to-noise ratio. This metric should be around a few decibels maximum to ensure a quality receiver. The lower, the better. Image rejection is the ability for providing attenuation on the incoming signal and the image frequency by the RF amplifier. It should be around 50 to 60 decibels. The bigger, the better. Question: Receiver, RX, specifications. Following is a list of some parameter values in dB scale. Match them with the receiver specification parameter they most likely belong to. Also, in the table you make, order the values in descending order of quality, that is, the better value for that parameter should be at the top. Solution: according to the previous slide, fill in the table. Also, as you can see, this is a coarse categorization, because some parameters values can belong to more than one specification. Also, pay attention to the units. Only the sensitivity has a power unit, the others are just unitless ratios. Example: amps, advanced mobile phone system. Amps, analog cellular communication system, went into operation in 1983. Counterpart in Europe is old GSM. Analog modulation is used for voice transmission. Frequency shift keying, FSK, is used for data transmission. Voice bandwidth is limited approximately to 3 kHz. FM modulator designed to have delta F equal to 12 kHz. Approximate transmission bandwidth is twice delta F. 30 kHz channel spacing. 30 kHz channel is assigned to each user per direction, 30 kHz for downlink, and 30 kHz for uplink. Division of the spectrum, frequency division multiple access, FDMA. Downlink and uplink channels separated by 45 MHz over 824 to 894 MHz band. Example, GSM, newer, uses FM but more complex multiple access techniques, TDMA. Uses digital signaling, voice signal converted to a digital bit stream, each bit represented by a rectangular pulse. Rectangular pulse waveform being message signal M of T of FM signal. Before transmission pulse waveform might be pulse-shaped in order to reduce distortion in the channel, smooth pulses. By setting the sensitivity constant, Kf, of FM signal, to pi/2. Digital modulation is called Gaussian minimum shift keying, GMSK. GMSK signal of GSM has 200 kHz bandwidth, compare 30 kHz in EMS. Using time division multiplexing, TDMA, in GSM, 32 voice calls may shape 200 kHz bandwidth. 30/200 times 32 is equal to 4.8 more efficient than EMS. Example, GSM, frequency bands. GSM standards. Question, pulse shaping. From the previous slide, find the 30 dB bandpass bandwidth values for the rectangular pulse spectrum and the shape pulse spectrum, Gaussian pulse, and compare them, which one is more bandwidth efficient. Solution. Bandwidth of the rectangular pulse is 0.4 MHz, and bandwidth of the Gaussian pulse is 0.35 MHz. Therefore Gaussian pulse is more bandwidth efficient, given that their pulse durations are equal. Question. GSM, frequency bands. From the table for frequency bands for GSM, find the bandwidth allocated the GSM band of interest. Then divide this band to our bandpass bandwidths of rectangular and Gaussian pulses.